Hello, welcome to this video. In this video, we'll be looking at implicit functions. So the term dy dx simply means the operator d dx working on y, the derivative of the function y with respect to x. Now we saw that from the chain rule that if y is a function of, say, another variable t, then this would be the same as dy dt multiplied by dt dx, where y is a function of t, and we can write t as a function of x. Now, how about if we wanted to differentiate with respect to x a certain function of y? Similarly, we would first differentiate this function of y with respect to y, and then multiply by the derivative of y with respect to x, which is dy dx. Let's check this out for a few examples. So if we were differentiating 2y with respect to x, this would be the derivative of 2y with respect to y first, multiplied by the derivative of y with respect to x by the chain rule. We know that the derivative of 2y with respect to y is simply 2, and we don't exactly know y as a function of x, so just write this as dy dx. So the derivative of 2y with respect to x is simply 2 dy dx. Okay, how about the derivative of a function, let's say y cubed plus 12y squared with respect to x? This would be the derivative of that function first with respect to y, so the derivative of y cubed plus 12y squared with respect to y, then multiplied by dy dx. This is going to be 3y squared plus 24y, all this multiplied by dy dx, and that would be the derivative of that function with respect to x. Okay, how about for a product? Let's check this out for a product. So say if we had the product xy, then we'd have to use the product rule. So the product rule tells us that we'll take one of the functions and multiply it by the derivative of the other, and then add this to the vice versa of what we've just done. So that would be the derivative. Now the derivative of y with respect to x is simply dy dx, but from what we've just learned, we could say that it's the derivative of y with respect to y multiplied by dy dx plus y times 1, because the ddx of x dx is simply just 1 from the rules of differentiation that we already know. So this would be x dy dx plus y, and that would be the derivative of the product xy. How is this useful? This knowledge is useful in differentiation of implicit functions. An implicit function is one in which y hasn't been explicitly expressed as a function of x. In other words, if we have the function y squared is equal to yx plus 3x squared plus x minus y. In such an equation, it might not be easy for us, to write y as a function of x. In other words, y is equal to, a certain function of x. Yeah. This is different from the function, say y is equal to 3x, where you can say that y has been expressed explicitly as a function of x. Here, to get the derivative, we'll simply just differentiate the right-hand side. Of course, you're also differentiating the left-hand side, but it's straightforward in that sense. So this sort of knowledge helps us to differentiate functions like these, and hence get our gradient function. Let's look at an example of that. So we've been asked to find dy dx given this equation. This is the equation of a particular function. So what do? We differentiate both sides with respect to x. So we'll have d dx of x squared plus y squared minus 6xy plus 3x minus 2y plus 5 is equal to the derivative of 0 with respect to x. So differentiate term by term. When you differentiate x squared, you get 2x. When you differentiate y squared, you know that you get 2y dy dx from what we've just seen. When you differentiate 6xy, this is a product, and we saw that when you differentiate xy with respect to x, you get x dy dx plus x dy dx plus y. So I'm just going to write that there. When you differentiate 3x with respect to x, you get 3. 2y with respect to x, you get 2 dy dx, and 5, you get 0, and you have a 0 on the right-hand side as well. We can collect like terms. So all the terms that have dy dx, we can have them together. 2y minus 6x minus 2. All this multiplied by dy dx. We take everything else to the other side. We have negative 2x plus 6y minus 3. And so dy dx will be equal to negative 2x plus 6y minus 3. This is divided by, we could factor out the 2, y minus 3x minus 1. And so this would be the gradient function. Realize that in this case, the gradient function is dependent on x and y, which is a common case for such functions. And so to find the gradient function at a particular point, we would need both the x coordinates and the y coordinates. So this is how we use implicit differentiation to find the gradient function of implicit functions.